Assalamu alaikum and welcome to the Reaction Engineering Lab course. Now today we are going to go through the general introduction of the lab and the activities, how to plan, what to do, and how to find out the unknowns that we are looking for. So first thing I need to ask the question, what is the objective? The objective of this lab is to enable or to train the student to identify, plan and design any experiment that they need to find out the kinetic parameter for any experiment. So kinetic parameters are usually what is the order of reaction, what is the RNS constant, what is the activation energy constant, and the values. So what you do in the course, we want to do some experiment for a particular system or particular reaction, which in our course is saponification. So we are going to do ethyl acetate react with NaOH to form sodium acetate and ethanol. Okay, so in this one what we need to do is we want to find out what is the kinetics. That means what is the order with respect to ethyl acetate, what is the order with respect to NaOH, and what is the activation energy and RNS constant. The four parameters I am looking for. Okay, this extended experiment, so is well known, values are available in literature, so that's why we have chosen this one. Now to achieve the kinetics, what I have in the lab, we have 5 different type of reactors. A batch reactor, a CSTR reactor, a plug flow reactor, and laminar flow, and plug flow with a packing also. So it's like 5 reactor. The question that I need to ask is, do I need 5 reactors? The answer is no. But why we are trying to learn all the 5? Because I as a student, I as a professional, when I want to design the experiment, I can choose which to use for what purpose. Okay. So in the lab we are going to at least use the 3 of them, the batch, CSTR and the plug flow reactor, or the laminar flow reactor if you want to call, to help us to get the enough data to find out the kinetics. Okay, so this is the reaction that we have. So sodium hydroxide reacting with ethyl acetate going to give you sodium acetate and the ethanol. Now if I want to write the rate equation for this one, then it will be R either ethyl acetate minus, because getting consumed, NaOH also getting consumed, so KCACB. A is NaOH and B is ethyl acetate. So the order of with respect to this one is alpha, the other with respect to the other compound is beta. So this one, and then K further is basically A naught exponential of minus EORT. That means we have 2 more unknowns here, A naught and EA. So altogether basically I have 4 unknowns in my reaction here in this equation, A naught, EA, alpha and beta. I want to design experiment, I want to conduct experiment so that I can find these 4 unknowns. How I can do that one? By conducting experiment, and experiment we can conduct so that we can follow the concentration versus time data, and then concentration is basically indirect measurement of you can say conductivity. So in the equipment we are going to measure the conductivity with time, so that we can then use the equation to convert into concentration, so that we'll know that how the concentration is changing. You have 4 unknowns, the alpha, beta, order with respect to A, which is the ethyl acetate, order with respect to NaOH. Then you have A naught, the and EA, activation energy. So what I need to do is I can think of, to find 4 unknowns, I need to run at least 4 or 5 different experiments. Yeah. So if I do an experiment where I keep 3 of the condition constant, then I can evaluate the A. And if I do the otherwise, like if I keep first 3, then I can keep this one. So in this way I can think that what is the experiment that I needed and which reactor will be more favorable to that one. So accordingly we can choose. How we need to do? We will always try to find the easiest variable first, and the easiest variable is the order of reaction. So we will first find the alpha and beta. How we can do that one? So you have 2 compounds. If you can make one excess, so the order of reaction will be effectively from the other compound. So that's what we'll do. We'll do the reaction one experiment where the concentration will be equal, both compounds, and one will be excess. So we'll compare with this one, and we'll find what is the value of alpha and beta. Then we will do the same experiment under different temperatures, so that we can plot and take the slope and intercept to find the value of EA and A naught. We have the batch reactor here first. So what we do, we take two equimolar concentration, which is 0.1 N NaOH and 0.1 N actually the ethyl acetate and NaOH, both of them we move it here and then allow it to react. So what will happen? Initially the concentration is high, so the conductivity will be high, and as the time progress, conductivity will go down, it will stabilize where the maximum once it's reached equilibrium. Yeah. So right now I can see this one has stabilized around 0.1 millisiemens per cement. So this is my final conductivity. So from here, when I put 2 equimolar solution, so I get, when I plot, I get the value of alpha plus beta, which is going to be 2. And how will we get that value? We take this concentration with time data, and then we try to use the integral method, in which we use 0 order, first order, second order, third order, and check which one is straight line. So in this case it will be second order, that will be straight line. So we'll know that alpha plus beta is 2. Then what I do, actually I just drain that one. I put another sample in which one is excess. So we took ethyl acetate in excess and sodium hydroxide 1/10 of the concentration. So sodium acetate will be the sodium hydroxide will be 0.05, and the ethyl acetate will still be 0.1. So what will happen actually is the conductive is like there is a 10 times difference in the concentration, so one is in excess. So effectively now the same again I am generating the concentration with the time data and plotting and checking the which one fits 0 order, first order, second order, third order, and I will find that this is 1 order, first one, that means with respect to that which is in excess is 1. So the other one, that means first experiment I got with the equimolar 2, this one with 1. So I can just do that the math to get the other one. So 1 and 1 with each other. So that's basically help me the batch reactor. Actually the other the unknowns, which are the temperature, at different temperature used for the activation energy and RNS constant, that also I can do. So the equimolar feed I can take again and do at 25 degrees C and find what is the plot to find the slope. Then I do another one at different temperature, another one at different 3 different temperature, I find what is the final conductivity and then plot it and get the slope. So this one, the slope will be basically my activation energy, and intercept will give me the A naught. So entire experiment I can do in the batch reactor, or I can do in the CSTR, or I can do in LFR or PFR. Okay. So it's just like whichever is easier for us, we follow that way. So I can do entire experiment here. So minimum to find out the 4 variables, how many experiment I will need: 1 equimolar at room temperature, 1 excess at the room temperature, maybe 2 excess I do. So one I do 0.1, which is equimolar, then I do 0.1 and 0.05, and then one more I do 0.1 and 0.01. So it's like 3, so that it's more accurate. So that will give me the 2 alpha beta. Then what else I unknown is my A naught and EA. To do that one, I do 3 different temperatures. So I can do at room temperature, then I can do 30 degree, 35 degree, 40 degree, 45 degree, as many plots, so that I can plot it and find what is the final conductivity for each one of them once it's decided, and then get the intercept and the slope. Intercept will give you the slope will give you basically the activation energy, and then that will give the A naught. So entire experiment can be done in the batch reactor. Okay. So let's just see how the batch the CSTR reactor and the other works. Okay, so this is my plug flow reactor. I can actually here as well, you can say tubular reactor. I have 2 more reactors which I can, if you see the basic unit, it has just this as a add-on. So I can remove it and put the batch reactor, or I can remove it, put the CSTR reactor. So the same base unit can work for any of the reactors. Okay. So what here we do, we take the feed A and feed B, equimolar them. So the same experiment that you want to do, equimolar first, put it here, let it allow it pass it through your inside the tube. You can see here there is now inside the bubbles going. So because the ethyl acetate and NaOH, they are coming here, getting mixed and then flowing through the reactor. So the reaction is taking place. By the time they exit, they will be in equilibrium. So we are measuring the conductivity at outlet here, and so at this much particular flow rate, at this temperature, I am measuring what is the final conductivity. Then later what I can do, I can change the temperature of my both of the feed, and again allow it to reach a steady state and measure what is final conductivity. So the same set of data we are collecting, final conductivity, the conductivity at equilibrium when the equimolar concentration is there at known temperatures, so that I can use them and plot to find out the EA value and the A naught. So that one, in case I want to also find out alpha and beta here, so what we do actually here, it's better there it's done, but here also I can do, I just take the known amount of sample that I want and then allow it to measure actually. So it's the same, but here it's little bit difficult to control. So that's why the batch reactor we use to find out the alpha and beta. The plug flow reactor and CSTR we use to find out the value of activation energy and E naught. This equipment is the CSTR, as we have already seen for the batch and the plug flow reactor, the laminar reactor. Here is our reactor. Again, this is a base unit on which you can put this one as a add-on for the CSTR, for the batch reactor, for the PFR, or anything. So we again have here two different feed basically tank, two pumps here again as the same. So the pump A will take the fluid here, pump B this one. So we can see here both the are coming here and then they are going in my reactor. So this is the entire reactor. As its name suggests, CSTR means continuously stirred tank reactor. So you have a tank, this is the glass tank, then we have a continuous stir, and we have the feed A and feed B both are coming and they are reacting. Okay. So what we are waiting actually is, we are waiting for it to fill the entire volume of the reactor so that they are in equilibrium. The moment A and B come, they interact, the reaction will start. Yeah. So we are basically measuring the conductivity here. Right now it's very low conductivity because I am just using a dilute or maybe just normal DI water I am using. So the conductivity is very small, so it's just 0.02. But when actual sample you use, you get conductivity around 0.8 or something that we saw there, 0.85. So again, now the four parameters that we have, if I want to evaluate them here, the first one, equimolar at the room temperature, that will help me to calculate the alpha plus beta, the overall order of reaction. Then I dilute one of them to make it excess, and then again do the same thing, run the experiment at the same temperature so that the A naught and EA is constant. And now in this case, because one is in excess, the order will come from the other reaction or reactant only, and that will be alpha. So with these two reactions you can do alpha and beta. Okay. If you want, you can further dilute it and do another 3 runs, so you double check and get more reliable data. That's the only thing we want to do. So that will help you to find the two unknowns. Then you want to find out maybe the other things, E naught and EA and A naught. For that one, now these two feed, one time allow them to do react and to reach state at room temperature, then heat them. Okay, here we can heat them. Here right now we don't have heater. The new one that we saw, the other one, they have built-in heater. So here if I want to do it at room different temperature, I have to heat in the external heater and then put it back here and let it again do the reaction, reach steady state, and then again do at least 3 different temperatures, then the final conductivity for each one of them. So at this temperature, this conductivity, this temperature, this conductivity, plot the curve, take the slope will give you the EA, intercept will help you to calculate A naught. Okay. So what I just tried to say is that you basically don't need all the 5 reactors to find out your kinetics. You can actually just one of the reactor is enough to do the entire set of experiments to find out that one, but we are spreading out so that you learn them all and then you can use whichever is available to you. So of course all the experiment when we do, everyone they have different advantage, disadvantage. For CSTR, for batch reactor, for plug flow or laminar reactor, they all have certain advantage, disadvantage. So as the purpose of the lab is to help us to help design, conduct experiment and find out the unknown kinetic parameters. Okay. So hopefully with this you will be able to design and come up with your things. If you want to do different, instead of 3 different temperatures, you want to do 4 different temperature. If you want 5 different temperature, instead of 2 different concentration, you want maybe 3 or 4, up to you. Yeah. So this is my laminar reactor here. So you can see here there is a vertical tube in which I am going to flow my 2 reactors in order for them to react. So the A and B, both of them, the ethyl acetate and then hydrogen hydroxide, they are entering at the bottom and they are flowing under pressure and going up, out from here, going out, and then we are measuring the conductivity here. Okay. This I can put it in the other setup to connect that one. That's the only thing. So what we are doing, we are allowing the reactants, both of them, to come into contact here, and then using the laminar flow to basically allow to maximize the contact between the two to have the more reaction, and once they come out, okay, they basically are in equilibrium, and we are just measuring from here what is the conductivity, final one. So if I want equimolar same concentration, I can do that one time. Then I want one at different concentration, one at maybe excess, again the same, and wait for that one. So the same for the LFR also, I can plan in a way that I can do the entire set of experiment here itself. So this was our LFR. Now if you want my plug flow reactor, so the plug flow reactor are basically two types which we have here. The one that we already seen was the pipe or the tube. Yeah, here we have packing. So again the same logic applies. So you have feed A, feed B, both are coming here, they are coming in contact, and they are basically flowing through the void, or if you want to call, or the space that is available for flow, and then they are going up, coming out from here. By the time they come out, they are in equilibrium. So we measure again the conductivity from here, which is from the outlet, and we find out what is the unknown. One experiment I do at room temperature, another one I can do when I have high temperature, another one I do another temperature. So 3 temperature and final conductivity, plot the temperature versus the conductivity, and take the intercept and slope to find out the value of Arrhenius constant and the activation energy. So this is from here, the same from here, or from here. The theory is same, logic is same. It helps me to plan, identify, and help me to calculate the unknown kinetic parameters.